Last time we talked about light in terms of its wave nature, but some things about light aren't exactly explained by its wave nature. For example, the wave model of light can't explain why certain things when they're heated only give off specific wavelengths of light, or why some metals give up electrons when they are subjected to particular frequencies of light. So, the theories about the nature of light had to be tweaked just a little bit. We're going to talk about that in this video. Let's go. We've already observed that when certain elements are heated, they will glow with a particular wavelength of light. Some substances, though, can give off more than one color depending on the amount of heat involved. Iron, for example, can be heated to the point where it glows red. If we heat it a little bit more, it'll glow orange. So we see that at certain temperatures, iron emits one color of light, but then at another temperature, a higher temperature, it will emit a different color. These colors correspond with different frequencies and different wavelengths. Now, the wave model just couldn't explain these different wavelengths of light being emitted at different temperatures. So in 1900, a German physicist whose name was Max Planck began to study the light that came from these heated objects with their different wavelengths, different frequencies. This study allowed him to discover that matter only absorbs energy in specific quantities, extremely small specific quantities that we call quanta. One quantum is the minimum amount of energy that can be gained or lost by an atom. Now, this idea of energy being transferred in small infinitesimal steps was pretty revolutionary. Before that, it was thought that energy was absorbed in various amounts, that there was no real minimum to it. If we think about something like heating water in a microwave, for instance, what's actually happening to the water is that the water's temperature is increasing by the tiniest of steps, infinitesimal steps. That's because the molecules of that water are absorbing quanta of energy, one quanta at a time. But because the steps are so small, all we see is a continuous rise in temperature. You get it? In reality, the temperature of that water is increasing in extremely small steps, but steps nonetheless. Now, Planck was a smart guy. He was able to determine that the energy that comes from those hot objects, it was quantized. It was in discrete amounts. And so he came up with an equation to describe it. The energy of a quantum is directly related to the frequency of EM radiation involved. That frequency is multiplied by a constant that Planck determined. We call it Planck's constant. That constant is 6.626 times 10 to the negative 34th power joule seconds. Now, you might recall that the joule is a unit of energy. Depending on your particular frequency, matter can absorb energy in whole number increments of h times your frequency. This times this. One of these, two of these, three of these, you name it. It's like if you were taking wooden blocks and placing them on a scale. You can take off a block or you can add a block, but you can't add, say, a quarter of a block or a half a block. It has to be a whole block or nothing at all. So do you get it? Matter then can only absorb or release certain amounts of energy. There are no in-betweens. Another phenomenon that the wave model of light could not explain was something called the photoelectric effect. This is a phenomenon that occurs when a metal will emit electrons. We call them photoelectrons. But it will only do so when a certain frequency of light shines on the surface of that metal, or anything above that frequency for that matter. So how does the wave model fall short on this? Well, the wave model suggests that no matter what the energy, even a low energy amount of light shining on that metal would eventually cause some electrons to be released. But in reality, that's not the case. In reality, a metal will only emit those photoelectrons if there's a sufficient frequency of light involved. Remember, frequency equals energy. So there has to be sufficient energy to get those electrons to be emitted. Let's take silver, for example. Silver will only emit photoelectrons if it's subjected to a light that has a frequency of at least 1.14 times 10 to the 15th hertz. Anything less than that, and no photoelectrons are released. So what is it? Is light a wave? Is it a particle? Who knows? Einstein, that's who. So Einstein came along and said, hey, let's have the best of both worlds. Light is both a wave and a particle. That's right. In 1905, Einstein proposed that light has a dual nature. It has both wave-like and particle-like properties. To make this idea come together, Einstein proposed the concept of light being like a beam of packets of energy called photons. And a photon is simply a massless particle that carries one quantum of energy. Knowing that a photon contained one quantum of energy, and also knowing that Planck's equation covered the energy within one quantum, Einstein used the equation to determine the energy of a photon. It's basically the same equation. The energy of a photon is equal to Planck's constant multiplied by the frequency of EM radiation in that photon. So if a photon with sufficient frequency strikes that metal, even at a low intensity, it will still cause that ejection of a photoelectron from the metal. So because of his work with the photoelectric effect, Einstein won the Nobel Prize in Physics in 1921. Do you remember when we did the flame testing at the beginning of our previous video? That idea of elements giving off only certain frequencies of light is another reason why the wave model isn't entirely effective. Remember when I used this spectroscope to take a look at the sunlight, and we saw that there was a continuous spectrum of color inside the spectroscope. If I use this again, except looking at the fluorescent bulbs above me, I get a different spectra altogether. In this case, I only see 5 particular lines, 5 particular wavelengths of light. And that's because the elemental vapor inside those fluorescent bulbs only gives me a few specific wavelengths of light. We can see some red, some gold, some green, some lighter blue, and some violet. When atoms absorb energy, they become excited. The electrons in that atom move further away from the nucleus, giving them a higher level of energy. They don't like to stay there forever, so they release that energy and come back down, and each element has its own fingerprint of combinations of wavelengths of light that it emits when it releases that energy. We can only see those individual wavelengths of color if we allow the light from those excited atoms to pass through a prism, and then we can see the individual wavelengths that are emitted by those excited atoms. We call this the atomic emission spectrum. The atomic emission spectrum is the set of frequencies of EM waves that are emitted by atoms of that element. In the case of the fluorescent lights, there's a tiny bit of mercury vapor that's responsible for the light coming from those bulbs. When the light passes through the prism in my spectroscope, then it's divided. I can then see the individual wavelengths involved in that light being produced. Unless I have the prism, my eye sees all the colors together, and I see white light. But again, in actuality, there's only a few distinct wavelengths of color. By the way, we can also have something called an atomic absorption spectra. And this is basically the opposite of the emission spectra. In this case, you have a spectrum with very small gaps indicating the lines or wavelengths of color that the atoms of that element actually absorb. But I can't stress this enough. Each element has its own set of wavelengths that it absorbs and emits. How does that happen? Well, here's how it happens. Let's take hydrogen as an example. I'm going to show the energy levels of hydrogen. Now, I could show them as levels like this, round like you would expect. But if you don't mind, to make things a little easier, they're just going to be flat, the distance away from the nucleus. So as you can see, the distance between energy levels isn't the same throughout the hydrogen atom. There are different gaps in energy from one energy level to the next, and so on. We also need to remember that there is no middle ground in terms of energy absorption. Remember that? So an electron will only be found at exactly one of these energy levels, never in between. That means it has to be able to absorb a color that will put it exactly from one energy level to another. Let's talk about how precise these electrons are in what they absorb, or what they emit. Hydrogen, for example, only absorbs 4 distinct wavelengths of color. There's a wavelength of violet that it will absorb, about 410 nanometers. And then there's a wavelength of bluish violet, about 434 nanometers that it will absorb. Then there's one that's kind of a bluish green color, 486 nanometers. And then there's a red color that it will absorb, 656 nanometers. But here's the thing, it won't absorb anything else. Why? Because none of the other colors match the jumps in energy from one energy level to another. Take the jump from level 2 to level 6, for instance. That energy distance corresponds with the frequency of a photon of that violet light at 410 nanometers. That's it. Nothing else will do. Take the jump from 2 to 5. That energy jump corresponds with the frequency of a photon with wavelength of 434 nanometers. And that's it. Nothing else. From 2 to 4, we have an energy jump that corresponds with the frequency of a photon with wavelength of 486 nanometers. And then finally, from 2 to 3, we have an energy jump that corresponds to the frequency of a photon that has a wavelength of 656 nanometers. Isn't that amazing? Only those 4 wavelengths will do for hydrogen. And because of that, hydrogen's light that it emits is sort of a magenta or a light purple in color. Makes sense, right, when you consider violet and blue and red as being the main colors involved. What about orange? Why won't hydrogen accept orange? Because the orange frequencies won't correspond with the energy jumps that hydrogen has. Or anything green, or anything yellow, and only, as we've seen, just a couple of blues and 1 violet. That's all it can do. And the reason why the fingerprint changes from one atom to the next is because the distance and energy levels changes. This one is a representation of mercury. You can see there are different energy jumps, and so because of that, there are going to be different frequencies of photons that are absorbed by those electrons. So an electron sitting at one energy level will absorb a particular photon having a frequency that corresponds with an energy jump that it can do, and once the electron gets to the excited state, it will then release that energy in the form of visible light. By the way, it's not only visible light that can be released. Remember, we have a huge EM spectrum to cover. Going back to the hydrogen, you can see that if we have a jump that's somewhat larger than the energy jump that we had for violet, then we're going to be into the ultraviolet range, which means we won't be able to see that emission, will we? And the same holds true for anything that's less than an energy jump for red. Infrared, we won't be able to see that either. Okay, I've got a problem for you before you go. Remember our equation for the energy of a photon, where h is Planck's constant and this is the frequency. I want you to figure out what the energy is of a photon if you have a wavelength of 4.15 times 10 to the negative 7th meters. Now, you'll have to find the frequency first before you can solve this problem, right? But remember, there's a way to do that, isn't there? The speed of light equals the wavelength times the frequency. So solve for the frequency, then you can solve for the energy of a photon at this particular wavelength. Let me know in the LMS. That's all we're doing for today. Today we talked about the particle nature of light, how we have these packets called photons that represent basically one quantum of energy. Those photons can have different energies depending on the frequency. And then we also talked about how electrons will absorb and release only particular photons depending on their energy levels within the atom. So, I hope it's been informative and helpful to you. If I could be of any assistance to you, let me know. Until next time, God bless.